often. Please take it away.
Thanks very much. So I know I'm the last talk, and I understand that I'm keeping you from the sun and the beer, so I'll try not to keep you too long, but on the other hand, I'm not going to talk as fast as I talked last night at the demos. This presentation is a follow-on from a talk I gave at Balasage a couple of years ago called Invisible XML, and these are two of the reviews that I got for that paper. It is clearly a submission that needs to be shredded, burned, and the ashes buried in multiple locations. And the other person said, I think the audience will eat him alive, but I want to be there to hear it. So, you know, I've got a clear run to the door here, so if you start getting crazy, I'll be out of here. And there was also a follow-up paper at Prague this year, if you're interested. So, Invisible XML, what is it? It's a generic method for injecting any parsable structure and structured document into the XML pipeline so that you're no longer restricted just to getting XML into the XML pipeline, but you can get anything that's parsable. And it's based on the observation that XML, if you look at it the right way, looks a bit like a parse tree. So your input might be a bit of CSS like this, and what you'll get is something that looks like this. But I demonstrated it yesterday, so I can demonstrate it again. So, for instance, if I say, parse expression. So, what this has done, what I've just done, is that string there is the string that is just read, and this is the XML that's come out. But if I go to that expression, and where's expression here? I should have had that ready. There, expression text. So I'll add a couple of brackets around this and save it, and then go back to my screen here. And what happens now, of course, is that the parse will be different. Instead of being a sum of the product and B, it'll be a product of a sum of A and the sum. So you can see I made that edit, and now the XML it matches the structure of that document. So if you were at the demos last night, you saw these examples working in live. So you can read URLs and programs and expressions. So let me just give you a quick overview of how the method works. So you provide a grammar of the structure that you want to parse. So in this case, a very simple grammar for expressions that allows you plus and minus and times and divide and brackets. And so then you use a parser to parse your input string, and you get a parse tree that looks like this in regular parsing. Now if I turn that parse tree on its side, you can already see, oh, it looks a bit like XML, and in fact, yes, you can just then serialize this parse tree as XML. And the problem is here that there are far too many elements, more elements that you're really interested in. And so what we need is a way of just, in the serialization, forgetting about the purely administrative elements. And you do that by marking the elements that you want to keep, and then when you serialize it, you just get the interesting stuff out, and then you can process that with XML. So it's parsing that I'm talking about. How does it work? So some of you, maybe a lot of you know how parsing works, but this gives you the background for the parsing method that I want to talk about. So parsing takes a string of characters like A times 3 plus B, and it recognizes the underlying structure, and then it returns a structured representation of that. Now, one of the most used versions of parsing methods is LL1. It's deterministic. And that's what the one is referring to. You only need to look at the next character in the input to decide what's going to come next. So you don't have to look far ahead in the input. You can just look at the next input character or next input symbol, and you know what you're parsing for the next section. This makes it very, very fast. It's order n, which means that if the input string is twice as long, the parsing just takes twice as long. So it doesn't slow down. It's a very fast parsing method. In fact, there's no faster than order n. So let me take an example grammar. So this is a very simple grammar for a programming language. So a program is a block, and a block is an open brace with statements and a closing brace. Statements is a list of statements with semicolon in. But a statement is an if statement, a while statement, an assignment, a call, or a block, and so on and so on and so on. Now, this is a fairly straightforward grammar for writing down, but the problem is it's not LL1. And the reason it's not LL1 is because both assignment and call can start with an identifier. So you've got variable equals expression, and variable is one of the possibilities for a variable is an identifier, and a call is an identifier followed by the parameters. So in this rule, you don't know which of these possibilities to take just based on the next character, because of the next symbol, because it could, if you've got an identifier, it could either be an assignment or a call. So, but the important thing is that the language is LL1. So that grammar wasn't LL1, but the language itself was LL1. And how can we do that? Well, if we rearrange the grammar so that if you've got an identifier, then it's assignment or call, and then the assignment and call, you've got an identifier followed by something, the tail, and that tail then is either an equals, an expression, or a bracket in the parameters. So in other words, now you do know at each step, based on the next character, or the next symbol, what it is that you're parsing. So it's gone back, the grammar is now LL1, so the language is LL1. So you can still use an LL1 parsing method on it. Now, LL1 is popular, not only because of its speed, but also because of the ease that you can transform the grammar directly into code. And I'll just show you some examples here from the grammar that we're using. So a block, a program is just a block. So the procedure for program just calls block and nothing more. A block is a brace followed by statements followed by another brace. And so it's just expect a brace, then the statements, and then expect a closing brace. And so on and so on. The interesting one here is the statement. So as I said, you can decide based on the next symbol which of the sub procedures you're going to call. So if the next symbol is an if, then you call if statement. If it's while, then you call while statement. If it's an identifier, then identifier a call. If it's a brace, then you call block. And otherwise, well, none of the options match, and so you can then say, well, there's a syntax error. Of course, if you're going to make an industrial strength parser, you're going to add lots of stuff like error recovery and so on. But this is the basic method. So that's one of the reasons it's popular, because you can convert it just to code, but you don't have to, because you can also interpret the grammar. So in other words, you look at the grammar as if it were a programming language, and you do exactly the same as we just did in those code segments, but you just interpret. And I'm not going to go through this, but it does essentially the same thing. It decides on which alternative to execute based on the next symbol, and just carries on. So in fact, this is the whole LL1 parser, except for administrative details. So it's very, very small. This, of course, will be slower, but not that much slower. So what this means is that you can see a grammar actually as a sort of declarative programming language, if you like, for parsers. And declarative is where you say what you want, but you don't necessarily say how you want it to be achieved. So you see a grammar rule specifies a procedure. Each rule has several alternatives. Each alternative specifies a list of instructions, you could say, and those instructions are either a procedure call or matching a bit of the input. Now, so LL1 is popular, but it does have some disadvantages, and that's what I'm trying to show you now, is that you can only parse restricted languages. Only if the language is LL1 can you parse it with an LL1 parser, of course. And what I've hoped I've demonstrated as well, it also requires some skill and experience to write the grammar, because if you just write it down as an inexperienced grammar designer, then you might make mistakes like as was shown in that first example. So that's why I want to talk about Earley, which is an alternative parsing method. It's classical. I mean, it's very, very old, really. It's been around for a long time. And the nice thing about Earley is that it can parse absolutely anything. There are no restrictions as long as it's context-free. The problem is that it's not so popular. And I don't know exactly why, but I suspect that one of the reasons is that its worst case parsing time is order n3, n cubed, which means that if the input is twice as long, the parsing time is 8 times as long. So that puts a lot of people off. But what people don't seem to realize is that that figure is a function of the language and not of the parsing algorithm. That is to say, if the language itself is LL1, then Earley is also order n, so it's just as fast as the traditional LL1 parsers. So in other words, it's only the language that means that the parsing is slow and not the method in itself. Now, people find Earley hard to understand, and that included me. I studied it a lot. I knew how to write an Earley parser, but I didn't understand exactly why or how it worked. And the conclusion I came to was that that's because all the descriptions of Earley are in terms of its procedural implementation. And it doesn't explain what the abstractions are. It doesn't give a declarative intent of the whole. And that's what I want to talk about today. Now, Earley Works is an interpreter for grammars, just like the one I showed you earlier. And it should be clear that if you're trying to interpret a procedure like block, well, if you just got to follow those steps one by one. There's no big deal. But it's only when you get to a decision point here that parsing gets difficult, that you have to do something special. And that is where Earley gets clever, and that's what I want to talk about. But first, it's Sunday afternoon, so I want to make it a little bit lighter, with a little bit of an interlude, a related interlude, but all the same, an interlude. So, a current desktop computer runs at 3 gigahertz. Now, that's an interesting number because that means that the clock on a computer ticks as many times per second as the clock on the wall ticks in a person's lifetime. So, in other words, 3 gigahertz is a very big number. And some of us only manage 2 gigahertz, and my mother has already managed 3 gigahertz, but it's a sort of ballpark figure. So how can we understand what 3 gigahertz means as a number? What we're going to do is we're going to slow the computer right down to 1 hertz. So in other words, the clock on this computer we're now talking about is ticking at exactly the same rate as a clock on the wall. It's still very fast, mind you. It can multiply 2 18-digit numbers in 1 tick of the clock, in 1 second, which none of us can do. So there we've got our CPU with its registers happily multiplying away at 1 hertz rate. But at a given moment, it's going to have to get something from the memory. Now, want to guess how long it takes to get something in the memory? And on this, who thinks that it might be longer than a minute? 3 people. 10 seconds? Who thinks it's going to be longer than 10 seconds? In fact, 6 minutes. A typical, at this rate, a typical desktop computer will take 6 minutes of time to go and get a value from the memory. And in fact, much of the complexity of modern computers is purely about dealing with this bottleneck by doing parallel instruction decoding, data streaming, and all sorts of stuff. And caches. Typically, there are 3 levels of caches. You'll see that they get around 10 times bigger at each level. So each one is much faster, much smaller, and much more expensive than the next one. So with any luck, your data is only 3 seconds away. But if it's not in the in level 1, then you'll try level 2, and so on. In fact, that happens in parallel. And in the worst case, then, you go off to memory to get it, and then it'll be put in one of the caches. But, so we've dealt with that problem using hardware, but at a given moment, the CPU has got to get something from the disk. Anybody want to hazard a guess how long it takes to get something from the disk?
5 hours. 10
5
years.
5 hours? What?
10 years.
10 years.
Is that an old-fashioned rotational disk?
Yeah, this is a rotational disk. Yeah, this is a hard disk.
10 days. At least a year.
Couple of days? Well, it's actually 1 to 12 months. Now, that's, of course, a long time, and that you're not going to solve very easily with hardware. In fact, it's the reason why you should get an SSD, because an SSD will only take 2 to 6 days to get data, so it really does make your computer faster. Before I go talking about the solution for these delays, let me just also tell you about connecting to the internet, and that will take 4 to 19 years to get to. And by the way, these are latencies. This is not the time to get the data, it's just the time for the first bit of data to start coming in. So in other words, these things take really, really long times for a computer. So the solution for those long delays is parallelism, pseudo-parallelism. You can't do it in hardware, so what we do is we load hundreds, in fact on this computer I've got 250 programs I just looked running parallel. They load all these programs into memory and they each get a small time slot. So one program gets a small time slot. Well, when I say small, short, it's in human terms, it's about a year or two in the 1 hertz computer. And in a time slot, that program can either run to its conclusion, or the time slot can end and then it gets shifted out and somebody else gets a chance. Or it tries to do something that would take a long time, and again it's stopped and put in the queue. So the programs are paused in the last case, added to a list of programs waiting to run, which can be ordered on basis of priority, and then a new program is selected from that list and run. So it gives the impression of lots of programs running simultaneously, and that's because it's running faster than we can see the difference, but it's pseudo-parallelism. So that's the end of my interlude. Now the thing about it is that that's exactly how Earley works. It uses pseudo-parallelism. When it comes to a branch, it runs all the options, doesn't decide on which one to take, doesn't make any decision at all, it just runs them all, and if one of them succeeds, or one or more in fact, then it just carries on, and if one of them fails because a character doesn't match, then it just dies. It doesn't get scheduled ever again. So in this case, for statement, there are 5 alternatives, so there are 5 tasks, 5 programs as it were, that added to the queue to be run. The tasks get run in a priority, and that priority is the order of their position in the input. So that earlier in the input, the tasks get run fast. So that means you only have to look at a tiny little bit of the input. You haven't got bits of program looking at all different parts of the input. They're just slowly working down the input stream. When a task is run, it can do exactly one thing. It can either finish because it's come to the end of its rule, as it were, and then it's succeeded. And what it does is then it returns successfully to its parents, and they get re-queued. It can start a new subtask, in other words, call another procedure. It can match exactly one terminal system, the symbol in the input, and if so, then it gets re-queued again, because you don't want to keep on going down the queue. You want there might be another task that's allowed to work on this symbol before the next one. Or it might try to match a terminal, fail, and then effectively die. It's not successful, and so it doesn't get re-queued. There's one other special thing about how it works. If the task is started at a position in the input, and exactly the same task is also started at that position, it doesn't start 2 copies of the task, it just keeps 1 copy of the task around, and then links to the parents link to that 1 copy. There are 2 reasons for this. Partly it's optimizing so that the same task doesn't get run twice, but actually it's also essential because it prevents infinite recursion. So that if one task immediately calls itself, it stops it from just getting lost in recursion, which is a problem with some parsing mechanisms. So I don't have time to go through this example in detail, but I will just very quickly show you an example. Here's our input, and we're going to deal with this. So what happens is that a task gets started, program, it started at position 0. This red thing is its program counter, showing where in the process it is. This is the only task, so it gets run, and it calls its only task is block, so that gets started at the same point, at point 0, and that's got three parts. So block then gets executed, and the first character it sees up at the top there is a brace. It matches the brace, so it moves the program counter. This doesn't get, it gets swapped out, as it were, but that's the only program that's still active, so it gets called again, and that calls statements. Statements has two options, so this and this. We're just going to look at the progress of the top one. So statement gets called. It starts 5 tasks, one for each of its possibilities, including assignment, which you will remember starts with identifier, and call starts with identifier. Now, three of those fail immediately because the input doesn't start with if, and it doesn't start with while, and it doesn't start with a brace. So that we've only got assignment and call left over. They both got identifiers. So assignment calls identifier, so that means that this one will not call identifier because this is already running at that position in the input. So this links to that one, as it were. So assignment gets run, starts identifier, call similarly gets run and wants to start identifier but doesn't. Identifier succeeds and returns to both of them, so that now both their PCs program counters are here, so they're running in parallel, as you can see. This one will now die because the next symbol is not after the A. The next symbol is not a bracket, but it is an equal, so this one will carry on. And so on and so on. So I'm not going to go through all these steps. You can follow it in the proceedings. But what happens is that at a given moment, expression succeeds for the 0. So assignment then returns to its parent, which is statement. Oh, I don't know what happened there. Where was I? So it starts, so it returns to statement. Statement is now finished, so it returns to its parent, which was statements. Statements successfully matches the semicolon. That returns, so then it calls statements again. Well, there's an empty statements after the colon, so that succeeds. That returns to block. That matches the last character, and that returns to program, and we're done. So, in other words, it's using exactly the same method of how operating systems run programs in parallel, and it's parsing the input in a parallel way. So the last step is that we want to get the parse tree out of this, and that's just following through the completed tasks. We just look for the completed task per program. We see that that's completed with block, so we can find the block. That has got statements and so on. We just trace down the completed tasks and we can construct the parse tree out of that. I'm not going to go through this. I do explain this in detail in the paper, and you can read it if you're interested. But in other words, this is how you serialize the tasks into a bit of XML. And as you can see, it's a very small piece of code. It's not difficult to do. And so this is the output that you get if you just serialize the tasks as I've just described them, and again, as I described at the beginning of the talk, by marking certain of these that you don't want them as part of the serialization, you get the simpler version at the end. So my conclusion is that Earley has had a bad press for a long time, probably because of its worst case results. But that was no fault of its own. In fact, it's a very simple and effective parsing algorithm that's actually easy to understand once you know what the abstractions are, what it's actually trying to do. The reason that it's such a good parsing algorithm is because it allows you to write your grammars without knowing very much about grammars. You can just describe the syntax of your documents and not worry about whether it matches up with a particular parsing algorithm or not. So this is part of IXML, invisible XML. At XML Prague, 2 people in the audience said, "Oh yes, I've implemented IXML," which I didn't know about, and one of them was using it already in a project for the Dutch government. So it seems like it's been picked up. So if there's anybody here who's implemented it or planning on to implement it, please let me know, because I like to keep track of who's using it. Okay, that's it. Any questions?
aren't this artificial values for the complexity of the algorithm because it's pseudo-parallelistic? So it would be that fast if we have quantum computers and real parallels.
No. It really is that fast. It's
Okay.
not made up values. No.
How does it relate to the algorithms used for processing regular expressions which handle ambiguity in that kind of way?
I honestly don't know what the relationship between those are, to tell you the truth. I have to admit that I find this much more manageable than regular expressions, because regular expressions very quickly get huge and hard and unmanageable. And this, because you can abstract bits away, it becomes much.
It's handling a richer grammar. It's
Yeah.
handling non-regular grammars.
Yeah.
So it's more powerful.
Yeah, that's right.
But at the same time, it has the same characteristic of handling ambiguity.
Yeah, that's right. Yeah, it does handle that ambiguity. In other words, it produces all possible parses from the string, which you then have to choose from. IXML just chooses a random one. It doesn't worry about which particular one.
So as an output, you get a forest.
No, as an output, you just get one of them. Just get one of the parses.
Okay.
A question for someone who doesn't understand either, but how would this compare with James Clark's SGMLS parser, which has to handle use maps and notation? I think was it notation and use maps?
I couldn't answer that here, I'm afraid. So I don't know. I'd have to do a study to tell you how it compares.
I don't know how it works, but SGML you could map. You could use a use map that could map the notation to anything.
Well, I don't know about anything. I don't know actually what class of language is SGML if you leave all the angle brackets and stuff off. What the class of languages are that it manages. I suspect it's more restricted than what this can do, since this can do anything. And I mean, I've seen people do interesting things with SGML in that way, but I don't know I don't think it's as general as being able to parse anything.
Okay, but it'd be quite interesting because I think if you took all your examples and put them to the NSGMLS parser,
Yeah.
and did the use map so that you mapped, say, a space or a curly bracket to the angle, start of the element.
Right.
You could probably parse all your examples and make SGML.
Some of them, at least. There's probably some context involved there that you lose when you do mappings like that. In this case, you can take the context with you, and so different braces can have different effects.
Okay. Thank you very much, Stephen.
All right. Thank you.